Here you see a metal strap, just simple framing strap, and it's rotating. It's rotating in the counterclockwise direction because clocks, I believe, run in this direction. Okay, so the question is, how could we represent the direction of the motion of this strap by a single vector? Okay, if I ask you what's the direction of the motion, or when I ask people what's the direction of the motion, let's go ahead and let it go like this, they're going to do something like this. Okay, well, this is not a single vector. This goes from here to here to here to here. Its direction is constantly changing, so this isn't a vector. We want to represent the direction of this motion by a vector. There's no vector in the plane of motion. This thing's moving in a plane, a horizontal plane, let's say. There's no vector in the horizontal plane that can represent this motion because whatever direction it might be moving in the horizontal plane at one instant, it's going to rotate and be moving in a different direction at another instant. So our only choice for a vector that represents the direction of this motion is going to be a vector that's completely out of this plane, which means it's going to either be up or down if the plane is horizontal. It's going to be perpendicular to the plane. That's the only vector that's totally out of the plane. Now, the convention that we're going to use is, depends on the fact that our x, y, z coordinate system, if it's a right-handed coordinate system, x has this orientation, y this orientation, z this orientation. Now, because of these orientations, it's going to turn out that we're going to choose the upward direction to represent the counterclockwise motion. And in a minute, I'll try to motivate that for you. Okay, in order to get this thing moving, I can come out to, let's say, well, let's put it in this direction. I can come out to, excuse me, it's allergy season. I can come out to this point and give the thing a push in this direction. Okay, now what I did was I exerted a torque on this thing. At this point of the course, we haven't talked about what torque is, but it's just what happens when you exert a force at a position relative to the axis. Now, there are two vectors involved in this process, and I'm going to use these Sharpies to kind of represent those vectors. Okay, here's one vector. It goes from the axis of rotation, and I'm not going to be able to hold these in perfect orientation, but you should be able to get the idea. It goes from the axis of rotation out to a point at which I apply another force. Okay, so if this Sharpie represents a vector applying another force, then we see that this Sharpie is right now in the positive, oriented toward the positive x direction. This one toward the positive y direction. I'll put these in the plane so it looks that way. So I have a positive vector here indicating the point at which I apply a positive force. When I apply a positive force at a positive position along the x-axis, positive force in the y direction, I then get a positive rotation. We'll call that the torque that applies this rotation. We'll say that that torque, being the product of a positive and a positive vector, is positive. What's the direction of the torque? Well, it's the same as the direction of the motion. A torque is kind of a twisting force, in the direction in which it twists cannot be represented by a vector in the plane of rotation any more than the rotation itself can be represented by such a vector. So the torque and the direction of rotation will both be in the positive z direction. So let's consider this picture. We have positive x, positive y, positive z directions with unit vectors I and j, which we've just seen, and a unit vector k in the z direction. And that's fairly easy to understand. Now, I want to define what I call a cross product. A cross product will be something that gives us, that would give us the vector indicating a torque if we multiply the two vectors that produce the torque. And you might not understand what I just said. I don't particularly like that statement. We're going to move on. Okay, so I cross J. Well, we've just seen that if we apply a force at a positive position in the x direction and apply a positive force in the y direction, we get a positive torque that's in the k direction. So the I cross J is going to equal k. Now, what if we applied a J and a K? Okay, I'm going to pause for a second. I want to think about a picture I might want to draw here. Okay, don't want to waste your time by drawing the picture while you watch, but the picture's fairly straightforward. Let this represent the strap. And let's just say that we start from the axis, we move out to a position along the J vector, and then we apply a force in the K direction. So you can see that in terms of the picture. Now, remember we said the counterclockwise direction is positive, so the orientation of this, we would have the J vector coming along here, the K vector here, and we would get, again, a counterclockwise rotation. That rotation would be in the direction perpendicular to the plane of motion, and that would put it in the I direction, so that J cross K should be equal to I. And you can kind of think this one through. I'm going to tell you that I cross K, that means we turn the thing this way. We have it let's say, along the x-axis, the axis of rotation being the y-axis. We come out to a point along the I vector, and then we exert a torque in the k direction. That's going to give us a clockwise rotation. Try to visualize that. So in any case, the I cross K then would have to be clockwise. Perpendicular to the plane of rotation would be in the direction of the y-axis along the axis of rotation, and that would be in the direction of the J vector except in the direction of the negative J vector. Now presumably you have a strap. I'm not sure I've given you an axle for the strap, but you can kind of play around with that and try to get that idea. Let me return to the physical strap here for a second. Assuming that this is the J direction, let's come out to a point J units from the axis and apply a vector I perpendicular to that. What's going to happen? If it's J cross I, it's going to tend to rotate the strap like this. That's in the clockwise direction, which is going to be negative. Now again, by playing around with the strap and making sense of the directions of rotation that we get, and you might or might not want to take the time to do that, but this is where the rules come from, and this is why they make sense. So we can see that J cross I would be negative K. And similarly, K cross J is going to be negative I, and K cross I is going to be positive J, because that's going to be the reverse of I cross K. In other words, when you reverse, when you change the order of your cross product, you get the negative of what you would otherwise get. Another thing that's fairly easy to understand, if I move to a certain point along my strap and then exert a force in the same direction, well, I can pull on this end of the strap in the direction of my displacement from the origin until the cows come home. And if the axis remains firm and the strap doesn't pull apart, and I'll show you I won't do that, it's not going to rotate at all. There's going to be no rotation. And from that we conclude that I cross I or J cross J or K cross K, ignore this little thing here, that's kind of permanent on the board unfortunately, but that any of those products, the product of any of these unit vectors with itself, cross product of any of these unit vectors with itself is going to be 0. Now with these rules, primary ones being these three, because we can see that reversal simply changes the sign of the product, and the idea that a vector crossed with itself has to be 0. Let's calculate A cross B for vector A equal 2i minus 3k, B equals 4i plus 3j plus 2k. Now I've written out the straightforward part of the calculation. I've just written A cross B is, well, there's the A vector, there's crossed with the B vector. Now, again, the algebra is very similar to just regular algebra with real numbers. We do have the fact that if you reverse the order of a cross product, you do reverse the result. So we have to be careful to use these rules correctly. But having written this out, we can simply apply the distributive law that this cross product should be 2i crossed with all this, 2i crossed with the B vector, minus 3k crossed with the B vector. And then we can distribute through that. We do have to be careful to keep the order of our vectors, of our cross products in the specified order. We have to order matters with cross products, as we've just seen here. So we do 2i crossed with this. We just distribute that cross product through. We get 2i times crossed with 4i. The 2 and the 4 are just scalars. They just multiply. We get 8. I cross I is I cross I. Now, that's going to be 0, but we're not going to deal with that in this step. We'll just do the distributive law. 2i cross 3j is then going to be 6. And then times I cross j. 2 times 2 is 4. I times k, I cross k is I cross k, etc., all the way to the end. The rest comes about in a straightforward manner if we just use the rules. I cross I is 0, so that's going to be the 0 vector. I cross j is k, so that's 6k. I cross k is negative j, so that's 4 times negative j. And then we have negative 12, k cross I. What's k cross I? Well, I cross k is negative j, and what did I just do? I did something wrong here. Hang on a second. Sorry, thought I made a mistake and didn't. Just got confused between this term and this term because of the alignment here. Okay, we got negative 12 k cross I. What's k cross I? K cross I is the opposite of I cross k. I cross k is negative j. So k cross I is just plain old j. Then we have negative 9 k cross j. And what's k cross j? Well, j cross k is I, so k cross j is negative I. And then k cross k is 0. And now we can simply collect our terms. 4 times negative j is negative 4j, minus 12j is negative 16j. Negative 9 times negative I is 9i. And we've got a 6k over here. So if I haven't made a mistake, there's our vector product.